Okay folks, this is our lab this week on diodes, and I hope that you have taken to heart the advice I gave you in class on Tuesday, that these videos are not meant for you to watch along and do the experiment with me as I'm doing it. It is intended for you to watch the video with the handout ahead of time so that as I am performing certain steps in the handout, you're able to see what I'm doing, watch it all the way through once, then go back and try to do the experiment. And if you want to have the video then, fine, but do not watch the video cold turkey and then think you're going to do the experiment correctly. That is a mistake, and you really should not be doing that. And so please try to be more careful about doing your experiments. And the apparatus for this week is actually pretty straightforward. We're not going to be using a whole lot of different equipment, but so it's pretty easy to do. One thing I will suggest at the beginning that we do is we've got our multimeter present here, and usually we've been using the probes that are both pointed. This week what we're going to do, or what I would suggest, it's going to make measurements a lot easier, is if you keep the red probe that is pointy and remove the black probe that is pointy, and just take it out of the way. And then in your multimeter case, you should have the alligator clip probe that we are able to use, and so I would suggest that we use that. You'll see why a little bit later, okay? But I've been thinking about this ahead of time in order to plan, and so the way your meter should be is that your black probe should be the alligator clip, and then your red probe should be the pointy clip. Okay, so that's the first thing. Second thing is that we're going to be making use of some components that are in our little plastic kit here, and the first one is a potentiometer. Now the potentiometer in your kit, I've tried to give you a picture in your handout, but it is unassembled in your kit. Okay, so it is going to look like this. It has has three legs on it. Two legs are on one side, one leg is on the other, and it says 10K on the top, and there's a little white indentation there. In the same little compartment with it should be a little knob, a little pin, if you will, and I'm having trouble getting mine out, but I'll dig in there a little further. And so I'm just going to have to pour it out, apparently. Didn't have this much trouble getting it out the first time. Alright, so the pin has a little indentation on it, and it basically just pushes straight into that potentiometer, so that when it's fully assembled, you should have a potentiometer that looks like this from a side view. Okay, and then from the top view, it should look, top view should look like a knob there. And as you'll recall, we talked about potentiometers in class, that basically this is a voltage divider. Okay, so it is a voltage divider that is adjustable. So we can change the ratio of R1 and R2 just by doing that. That's why we have the 3 pins. So the resistance across these 2 pins is 10,000 ohms. And I can confirm that just by attaching my multimeter to one pin, and then I connect the other one, and certainly it does show right at 10,000 ohms. But then I've got this little wiper pin here in the middle. So as I turn the rotor, it's moving a wire up and down the coil that's inside this potentiometer, giving me a variable resistance. So right now, if I were to clip to that pin, like so, without damaging anything, if I measure the resistance between this pin and the pin on the top, I get a resistance of about 3,000 ohms. That means that to the other pin should be about 7,000 ohms. Okay, but I can change that proportion, that ratio of resistances. So I've now turned the rotary knob a little bit further, and now to this one it's about 5.39 kilo ohms. To this one it is 4.72 kilo ohms. All right, so you see how that works, that it's basically just a voltage divider that we can use. All right, so you want to make sure you've got that available. We're going to be using some other components that are different today. LEDs, we're going to be using all 4 of them eventually, so you may as well go ahead and get those out. So a red, a green, a yellow, and a blue should be present in your kit. Okay, so just get all 4 of those out so that we are able to make use of those later. And so those are diodes that light up. There's also a diode, or actually 5 what are called signal diodes in here, or rectifier diodes. And because the contents of our box tend to shift around a lot in shipment, I can't tell you exactly which compartment they'll be in, but I will show you what they look like. And they basically look like black resistors. So they give the appearance of a black resistor, except there's a silver ring around one end of it. Okay, so it looks like that, and I'm not sure if that's going to focus properly, but you get the idea. It looks like a resistor that's black, but there's a silver band across one end. All right, so we'll talk more about that later. The other thing that we're going to need is a 220 ohm resistor. And so if you've got your resistors sorted properly, you're going to be able to pull one out, but you never take for granted what you think the resistance is. You're going to measure that resistance, and in my case, I'm getting 218 ohms, and I'm going to record that value because that value is going to be critical for me later on. Okay? So do not forget to record the value of your resistance. All right, well, we're going to go ahead and assemble the circuit, and I've given you both a schematic as well as somewhat of a breadboard diagram of what it should look like. And so it's not a very complicated circuit today. We're going to go ahead and put our power supply, and I'm just going to use my 9-volt battery again, as I have been using the last few weeks, as opposed to the wall wart. It's just convenient to use, especially if I'm away from an outlet. But I'm just going to plug that into the breadboard. Again, making sure that the plus terminal on the power supply is in the column with the red band here, the minus sign with the blue band on both sides. That tells me I've got it in proper. My breadboard is vertical oriented, and and I can read the numbers right side up there. And the first thing I'm going to do is to go ahead and place my potentiometer on here. Okay, now I couldn't find an illustration of the exact potentiometer we've got. This one is a little unusual in that it's got the 1 pin on one side and 2 pins on the other. Most potentiometers actually have all 3 pins in a row here on the same side, but this one's a little different, and that's okay. We can work with that. What we're going to do is we're going to have it span our channel. Okay, so what I'm going to do is I'm going to arrange it though so that the 2 pins are on the right side of the channel and the 1 pin is on the left. Now the spacing, if you look at it, they should go into 3 subsequent rows on your breadboard, and if you need to bend the pins a little bit to get them to line up properly, that's fine. But I'm going to be careful as I insert that, and if I need to bend my pins just a tiniest little bit to make sure that they fit properly, you may need some needle nose pliers. That looks like that's oriented correctly, and then I'm just going to go ahead and press firmly down into that. Okay, and I'm going to go ahead and start making some other connections here while we're at it. So I've got my resistor here, and just to kind of get it away from the potentiometer a little bit, I'm going to put this resistor further down the board. Okay, so my potentiometer is right here. I'm just going to come down a little bit further on the left side though, left side of the channel, because what we're going to do, and I'll go ahead and actually, before I put that resistor in, let me go ahead and illustrate how this potentiometer is working for us. Okay, so I'm going to go ahead and attach the upstream side of the potentiometer to our red positive lead, and I will attach the downstream side of the potentiometer. Okay, so this is on the right side of the channel. I've got the 2 pins, and I need to attach one of those to the plus 5 volts and the other one to ground. Okay. Now what I'm going to do next is measure the voltage on the left side of the channel. Okay, so I've got my multimeter ready to measure voltage. And what I'm going to do first is I'm going to turn the potentiometer all the way counterclockwise. Okay, I'm not going to force it, but when it stops, I'm going to stop. I'm going to power on my power supply. Okay, and you'll notice by the green light it is powered on. And if I take my multimeter and just measure the voltage right there on that pin, you'll see that it is 0 volts here on my multimeter. Okay, but as I turn my rotary knob on my potentiometer clockwise, you should notice that the voltage is going up. Okay, so I'm at 1/2 volt now, 0.6 volt. And so this gives me the ability, the potentiometer gives me ability to select a voltage that is lower than the 5 volts of our power supply. So that's why we're using a potentiometer today. It's really the means to give us a variable or an adjustable voltage. Okay, I'm at 1.634 now. When I turn the knob all the way to the full right, I should get right at 5 volts. All right, 5.03, which is the output voltage of my power supply. Okay, so that's why we're using the potentiometer today. It's really to give us the means to adjust the voltage that we're going to send to our resistor and diode combination. All right, so that's the beauty of that potentiometer there, of what it's able to do for us. All right, so it lets us adjust the voltage. All right, now with that done, so that you understand that potentiometer and why it's used for that, we're going to go ahead and put our resistor in place. And again, I'm going to go a little further downstream from the potentiometer, bend it over like so. And I'm going to take my diode. I'm going to start with this silicon diode, and hopefully we will have discussed this in class before lab. But the band, the silver band that goes around that diode, that is the negative side of the diode. So I'm going to have positive current flow coming from the potentiometer to the resistor, through the diode to ground. And since current only flows one direction, I have to be careful how I do that. So I'm going to make sure that the silver band side is downstream. So just like with the resistor, I insert one leg, or I can bend the legs first, and then go ahead and insert one leg, and then the other. And then I'm ready for some jumper wires. Okay, so I'm going to connect a black jumper wire from the downstream side of my diode to ground over here. And I'm going to take a red wire to remind me that the positive lead of my potentiometer here, that wiper, is what's providing the voltage and the current. So you see, it's not a very complicated setup at all. Okay, now we're going to be interested in making measurements of the voltage across the diode and the voltage across both of these. Okay, so the voltage across both of these is going to be our power supply voltage. Okay, and so that's why I suggested that we have our multimeter set up like this today. All right, so we've got the alligator clip, and I'm going to go ahead and connect it to a jumper wire, and I'm going to put the other end of the jumper wire right there downstream of the diode. Okay, now what this is going to let me do is whenever I want to measure the voltage across the diode, I take my positive voltage probe and I just touch that upstream leg of the diode. When I want to measure the voltage across both of these, I can measure, I'm going to move this jumper wire, I can just measure right there at the resistor. So you see, I can measure the voltage easily across the diode and across the resistor without too much difficulty. I'll move that leg there a little bit just so it's a little easier to see that I'm touching the diode here, touching the resistor there. Okay, so that's what we're going to be doing, is we're going to be making measurements of the voltage drop across the diode, and then we're going to be making measurements of the total voltage, and we're going to be constructing a plot, and that plot is going to be the current versus resistance. Okay, I'm sorry, not current versus resistance, current versus voltage. Okay, now in your handout I've given you a template for a table that you should be recording information on. Okay, and so that is not enough, there's not enough rows in that table. I was just giving that to you so that you would know what the best way to record this information. You can do it on paper. You can certainly do it in a spreadsheet because we're going to be doing some calculations in there. And then when all is said and done, you're going to be constructing a plot with voltage across the diode on the x-axis and the current on the y-axis. And it's going to show a characteristic curve that is different from that of a resistor. A resistor gives you a straight line. We're going to get a curve with the diode. Okay? So with that in mind, we're going to go ahead and begin. You'll notice there in step 3 that what we're going to do is we're going to start at about 50 millivolts. And so what I'm going to do is I'm going to actually place my multimeter positive probe against the diode to measure the voltage across the diode, and I'm going to be watching up here, and I'm going to gradually turn the potentiometer until I get to roughly 50 millivolts. Now, if it's not exactly 50, it's okay. It doesn't have to be exactly 50, but just get in that ballpark. If it's 55, if it's even if it's 60, it's not that big of a deal. In fact, I'm struggling to get it here to 50 millivolts. So let's bring it down, and if you can't, then just, in fact, I'll modify the procedure to say start at 100 millivolts. Okay, so whatever that number is, all right, in my case it's 99.0 millivolts. Okay, that's 0.9 or 0.099. That is the voltage across my diode. That's what goes into that first column. Okay, so where it says V diode, in my case, this is 99 millivolts or 0.099 volts. Without changing anything, I'm going to measure the voltage across the resistor. And it's actually the same value. Okay, 99 millivolts. Now you can ponder why that would be the case. Okay. All right, I'm going to go back and then I'm going to increase this by roughly 50 millivolts. So now I'm going to be aiming for about 150. Okay, and I'm right there at it. Okay, close enough. 148.1. All right, 0.0. It's stabilized. Actually, let's wait a moment till it stabilizes all the way. 147.8. Okay, now I'm going to record that and I'm going to measure across the resistor. 147.6. All right. Now, if you do get into a situation, in fact, I wouldn't record all 4 significant figures here. I just record 3. But for these first few data points, the voltage across your resistor should be the same as it is across the diode, and so don't record a value less than the voltage across the diode. Okay, so if this is 147.1 and I come over here and it's not 147.1, it's 147.0 or 146.9, record what the voltage was across the diode, because that's just a measurement error. Okay, that's all that is. All right, I'm going to continue. I'm going to go up to 200 millivolts, give or take. And I may take a little bit of a fine tune here, so close enough. 191.5. Measure the voltage across the resistor, 191.5. Okay, and you're going to keep doing that. All right, so I'm not going to keep belaboring the point, but that's what you're going to be doing. And so voltage across the diode, total voltage. Now the voltage across the resistor is the total voltage minus the voltage across the diode. That's what I've set up here in step 4. The current then is going to be the voltage across the resistor divided by your measured value of your resistor. Now mine a while ago was 218 ohms. You need to measure what yours is and calculate the current and populate that table. And what you want to do is continue going, and eventually you're going to reach a point where you're going to max out your potentiometer and the voltage across your diode's not going to go any higher. Okay, and that is pretty common. Okay, that's the characteristic of a diode. That's what it does. Okay. All right, having done that, every diode does not have the same characteristic curve. So you're going to keep the same resistor. I'm going to power down. I don't tend to want to remove things otherwise, but we're going to take out that diode and we're going to put in one of our LEDs. It doesn't matter which one, but we're going to put one of those in. Okay. And I'm just going to start with the blue one. It's pretty bright, and by now you've learned the flat side of the plastic case is the negative side of the LED. So I'm going to put that in there because the legs are kind of spread apart a little differently here. I'm going to move my ground and my probe leads up a little bit. I'm going to turn it on. I'm going to turn the potentiometer up just to make sure that the LED comes on, because if not, that means I've got my wiring backwards. Okay, you can tell it does. There's a little neat property here. I'm going to turn this potentiometer left-handed so you can see it. I don't know if it's going to show up on the video this way, but if you turn the potentiometer slowly enough, even though you see it's lit right now, you reach a point where the brightness seems to suddenly increase rapidly. Even if you're turning the potentiometer smoothly, all right? Right there it happened, okay? And that's where the diode switches on all the way. And then it might get a little brighter after that, but not really, okay? And so anyway, you're going to make the same measurements for your LED as you did for that silicon diode at the beginning, okay? So the same thing again, but you're going to start at a higher voltage. Okay, so this time you're going to begin by having the voltage across your diode beginning at 1.5 volts. The LEDs have a higher switch-on voltage, so I'm going to go ahead and start by increasing my potentiometer until I'm at 1.5 volts. And you'll notice that my LED is not on yet. Okay, there's a higher switch-on voltage for it. And so that's 1.5 volts, and then the total voltage is also 1.5 volts. And then as I continue to increase the voltage in 0.1 volt increments, okay, so I'm going to go up to roughly 1.6, in this case 1.624, that's fine. And then I'll measure the total voltage again. And then as I get to the point where my LED starts to switch on, visually I'll be able to see it. Right there, for instance. And that's where my voltage across my total voltage won't be less than. It'll actually be higher than my LED voltage. So you're going to keep making those measurements, and again, all the way up. And once you've done that, you're going to reach the point where your potentiometer is all the way to the right, and you have maxed out at 5 volts total voltage. The voltage across your LED won't be the same. For the blue LED, it's going to be a certain value. But if you pull that blue LED out and put in a yellow LED instead, don't change the potentiometer, turn it on again, and if you measure the voltage across that LED, it's going to be different than it was for the blue. Different for the red, different for the green. And the reason is that they all have different switch-on voltages. Okay, and this creates some issues if you're trying to run multiple color LEDs because you have to realize that each one requires a different voltage before it switches on. They are voltage sensitive devices. They're not current sensitive, they're voltage sensitive. And so anyway, so that's really it for the experimental part today. And you know, I know it's a little tedious gathering the data, but gather the data properly so that when you're finished, you've got some very good graphs. I want to see a graph for your silicon diode. I also want to see a graph for one of the 4 LEDs. You don't have to graph the current versus voltage for all 4 LEDs, but you do need to do it for one. As I say at the end, I do expect you to write a comprehensive conclusion where you discuss LEDs. I want you to do some research on the various switch-on voltages for a common silicon LED, as well as for these 4 colors of LEDs. And I want you to do that in the literature. Give me the exact citation for what you found and compare what you measured against what you find in the literature. You're not going to have to write a theory or a materials and methods section this week, but I do expect to see your data. I expect to see any calculational results you've done. In fact, in your results section this week is where your graphs should be. Okay, so the data will just be the raw tables with your measurements. The results would be the calculations that have the voltage of the resistor and the current, and then the graphs of the voltage across the diode on the x-axis, current on the y-axis. Okay, and you'll do that for the silicon LED as well as for one of the silicon diode, not silicon LED, silicon diode, and then one of the 4 LEDs, whatever choice you want there. Okay. All right, that's it for today. This is a relatively short lab if you do it correctly. All right, but I want to see some good data, and I want to see some good conclusions where you do some research on LEDs, their difference in switch-on values, and if you really want to get into it, try to find out what semiconductor material they had to use to construct these various colors. Because I think I've mentioned before, the elusive color of an LED was the blue LED. That one has come about in your lifetime. And the man, or I forget if it was a man or a woman to be honest with you, but the scientist who discovered the proper semiconductor to give us a blue LED got the Nobel Prize for it. Because once we got that, then by mixing red, green, and blue, we could make a white LED. Okay, so very interesting. So that's lab for this week. Take care. We'll be seeing you in class. I'll be available by email if you've got questions. And for those of you who come to the live lab on Thursday, I'll be present to kind of help troubleshoot, but there shouldn't be a lot with the experimental setup this week. A lot simpler than the 555 timer was. So take care. We will talk to you soon.